In the YouTube video titled Lecture 20, Hash Functions by Christof Paar, Professor Christof Paar, a distinguished cryptographer, delves into the multifaceted realm of hash functions, elucidating their critical role within the intricate landscape of cryptography. The lecture commences by underscoring the indispensable nature of hash functions, highlighting their synergistic relationship with other cryptographic mechanisms such as digital signatures. Professor Paar then dissects the inherent limitations of employing the RSA algorithm for the authentication of voluminous messages, as it demonstrably struggles with the task of efficiently signing data exceeding the relatively modest capacity of 256 bytes. To circumvent this constraint, he introduces the strategic concept of integrating hash functions into the process. By compressing extensive messages into a more compact form prior to applying the digital signature, the lecturer argues, one can effectively mitigate the vulnerabilities and inefficiencies associated with direct RSA application. Paar meticulously outlines a comprehensive set of requirements for hash functions, emphasizing the need for adaptability to variable input lengths, the generation of concise and predetermined output lengths, and the paramount importance of expeditious execution. The lecture then takes a decisive turn towards the critical security properties that underpin the robustness of hash functions: preimage resistance and collision resistance. Through a series of illustrative scenarios, the professor vividly demonstrates the vital significance of these security attributes. He explicates how preimage resistance serves as a formidable barrier against adversaries attempting to forge messages possessing identical hash values to authentic ones. Similarly, collision resistance serves as a bulwark against malevolent actors seeking to exploit hash function vulnerabilities to generate distinct messages that share the same hash output. Drawing upon the foundational mathematical principle of the pigeonhole principle, Paar elaborates on the unavoidable presence of collisions within hash functions, arising from the inevitable situation where the quantity of input exceeds the available output space. This principle underscores the inherent limitations of any hash function, necessitating careful design considerations to minimize the likelihood of collisions and safeguard the integrity of cryptographic operations. The lecture further explores the implications of the birthday paradox, a compelling mathematical phenomenon that reveals the surprising speed at which collisions can be discovered. This paradox highlights the intricate relationship between the number of inputs and the probability of a collision occurring, with a significant increase in probability as the input size grows. In closing, Professor Paar underscores the paramount importance of designing and implementing hash functions that robustly resist collision attacks. He emphasizes the need for evolving hash functions to incorporate longer output lengths, thereby enhancing their resilience against the escalating sophistication of modern cryptographic threats. From 0 minutes to 5 minutes of the video, Professor Paar introduces the concept of hash functions as auxiliary functions in cryptography and underscores their significance in a wide array of cryptographic mechanisms, including digital signatures. He then uses the illustration of digital signatures to further motivate the application of hash functions, explaining that RSA, a prominent public key cryptosystem, can only sign a maximum of 256 bytes at a time. From 5 minutes to 5 minutes of the video, Professor Paar delves into the critical concept of hash functions, highlighting their pivotal role in cryptography. He commences by addressing the inherent limitations of RSA signature algorithms, specifically their inability to efficiently sign large files, such as PDFs. These limitations stem from RSA's blockwise nature, requiring the signing of individual blocks, making it computationally intensive for extensive data. To circumvent this obstacle, the speaker introduces hash functions as an ingenious solution. These functions efficiently compress voluminous data into considerably smaller fingerprints or message digests, thus enabling RSA to sign these condensed representations with minimal computational burden. Professor Paar meticulously outlines the fundamental desiderata for a robust hash function, emphasizing the paramount importance of preimage resistance. This attribute ensures that it is computationally infeasible to deduce the original message from its corresponding hash output, bolstering cryptographic security. Furthermore, the speaker underscores the significance of collision resistance, a property that renders it highly improbable to discover distinct messages that map to the same hash output. This resistance is crucial for thwarting attacks that exploit hash function collisions, such as those aimed at manipulating digital signatures. To elucidate these concepts, Professor Paar presents a compelling scenario involving a collision attack on a bank transaction. An attacker, Oscar, seeks to exploit a weakness in a hash function to manipulate a bank transfer by crafting two messages with identical hashes. One message is a legitimate transaction, while the other is a fraudulent request for a larger sum. The attacker's goal is to intercept the legitimate message and replace it with the fraudulent one, exploiting the hash function's vulnerability to pass the signature verification process. This attack underscores the paramount importance of collision resistance in ensuring the integrity of digital signatures and other cryptographic applications. Professor Paar illuminates the mathematical underpinnings of collision attacks, drawing upon the pigeonhole principle. This fundamental principle dictates that if the number of pigeons exceeds the number of pigeonholes, at least one pigeonhole must contain more than one pigeon. In the realm of hash functions, this translates to the unavoidable presence of collisions if the space of possible input messages surpasses the space of potential hash outputs. He then elucidates the relationship between the output length of a hash function and the probability of finding collisions. Specifically, for a hash function with an 80-bit output, there is a 50% likelihood of finding a collision when processing roughly 2 to the power of 40 messages. Professor Paar concludes the lecture by emphasizing the paramount importance of collision resistance in the design of secure hash functions. He acknowledges the ongoing efforts of the cryptographic community to develop new and more secure hash functions, illustrating the continuous evolution of cryptographic practices in the face of ever-evolving threats. He leaves the audience with a profound appreciation for the complexities and intricacies of hash function design, while underscoring their essential role in safeguarding digital data and transactions. From 10 minutes to 15 minutes of the video, Christof Paar elucidates the vulnerabilities inherent in a naive approach to signing long messages by segmenting them into blocks and individually signing each. He identifies 3 primary drawbacks. 1. The lack of comprehensive message integrity due to the possibility of an attacker surreptitiously dropping or rearranging blocks, thereby modifying the message without compromising the verification process. 2. The significant computational overhead associated with performing an RSA exponentiation for each block, rendering the process time-consuming for extended messages. And 3. The inefficacy of relying on asymmetric cryptography, which is considerably slower than symmetric cryptography. Paar highlights the disparity in attack complexity between the naive block-based signing scheme and the birthday paradox attack. The former exhibits a linear increase in attack time with the number of blocks, while the latter's attack complexity scales proportionally to the square root of the block count. Illustratively, an attack requiring 1,000,000 steps using the naive method would necessitate only 1,000 steps when employing the birthday paradox attack. To mitigate these issues, a cryptographic hash function is introduced as a means to condense the message into a fixed length before executing the signing operation. From 15 minutes to 20 minutes of the video, the speaker transitions from discussing the shortcomings of a naive approach to digital signatures to introducing the critical role of hash functions in addressing these limitations. They emphasize that hash functions are essential in real-world cryptographic implementations, particularly for tasks such as generating digital signatures. The speaker then delves into the fundamental requirements for secure hash functions. These requirements include the ability to handle inputs of arbitrary length, a fixed and concise output length, and efficient computation. To illustrate the concept of collision resistance, the speaker uses the scenario of a bank transfer where an attacker might exploit the fact that 2 distinct messages, one benign and one malicious, could potentially share the same hash value. The speaker then introduces the pigeonhole principle to explain why collisions are inevitable when dealing with hash functions. This principle, often referred to as the Dirichlet drawer principle, asserts that if more items are placed into containers than there are containers, at least one container must contain more than one item. In the context of hash functions, the speaker explains that if the input space is larger than the output space, then collisions are unavoidable. The speaker concludes this portion of the lecture by emphasizing that the goal of designing secure hash functions is not to eliminate collisions altogether, but rather to make the process of finding such collisions computationally infeasible. From 20 minutes to 25 minutes of the video, the speaker transitions to the third requirement for hash functions: collision resistance. He underscores that this is the most challenging aspect, elucidating its close correlation with the birthday paradox. The speaker illustrates this paradox by explaining that in a room of 23 individuals, a 50% probability exists that two individuals share the same birthday. He then introduces the formula for determining the likelihood of a collision occurring. He highlights that, for a hash output of 80 bits, finding a collision requires a staggering 2 raised to the power of 80 steps. To achieve the desired 80-bit security, he emphasizes that twice the bit length, or 160 bits in this case, is needed. To further clarify, the speaker employs the pigeonhole principle using an analogy of 10 socks and 9 drawers, demonstrating that at least one drawer must contain 2 socks. He succinctly conveys that this principle applies analogously to hash functions. The speaker underscores the critical importance of this requirement in the context of hash function security. He emphasizes that the following lecture will delve more extensively into this crucial topic. Finally, the speaker acknowledges that collisions are unavoidable due to the finite hash space. He asserts that the primary objective is to render finding collisions computationally infeasible. This challenge forms the bedrock of ensuring secure hash functions, he concludes. From 25 minutes to 30 minutes of the video, Professor Paar delves into the fundamental security desiderata of hash functions. Preimage resistance and collision resistance. Preimage resistance, synonymous with one-wayness, dictates that determining the original input from a given hash output should be computationally intractable. He then illustrates the concept of a second preimage attack, wherein an adversary, possessing knowledge of the original message x1 and its corresponding hash output, endeavors to discover a distinct message x2, yielding the same hash output. This underscores the necessity of second preimage resistance, ensuring that an attacker cannot generate an x2 that produces an identical hash output to x1. Professor Paar further introduces the birthday paradox, emphasizing its relevance to collision attacks. The birthday paradox, positing that within a gathering of 23 individuals, a 50% probability exists of 2 individuals sharing the same birthday, mirrors the challenge of identifying collisions in a hash function. He explains that attaining an 80-bit security level against collision attacks necessitates a hash function output length of at least 160 bits. From 30 minutes to 35 minutes of the video, Professor Paar delves into the second preimage resistance property of hash functions, a crucial aspect of cryptographic security. He employs the familiar scenario of a bank transfer to illustrate the concept. In this scenario, a malicious actor, Oscar, attempts to intercept the transaction. The initial message, transfer 10 euros, is denoted as x1, while the modified message, transfer 10,000 euros, is represented by x2. Professor Paar emphasizes the necessity of preventing Oscar from generating a second message, x2, possessing the same hash value as the original message, x1. He elaborates on this concept through a second preimage attack scenario. He posits that if Oscar were to successfully create x2, the altered message, it would appear indistinguishable from x1 to the receiver. This scenario underscores the importance of second preimage resistance, which safeguards against the unauthorized modification of signed messages. To further elucidate this principle, Professor Paar utilizes the analogy of a person with a unique birthday, July 18th, desiring to ensure no one else shares the same birthday. He introduces the notion of a birthday collision, which occurs when 2 individuals happen to have the same birthday. Professor Paar stresses that the likelihood of a birthday collision increases with the size of a group. Applying this concept to hash functions, he asserts that if a hash function has a limited output space, for example, 80 bits, there is a higher probability of 2 distinct inputs generating the same hash value. To exemplify this point, Professor Paar presents the formula for calculating the probability of a collision. He explains that if the output space is limited to 80 bits, identifying a collision would necessitate 2 to the power of 80 steps. Furthermore, he emphasizes that achieving 160 bits of security requires doubling the output bit length. This highlights the importance of selecting hash functions with sufficiently expansive output spaces to mitigate the risk of collisions. From 35 minutes to 40 minutes of the video, Professor Paar elucidates the concept of collision resistance, a paramount criterion for the robustness of hash functions. He expounds upon the principle that collision resistance safeguards against adversaries discovering distinct inputs that yield identical hash outputs. This imperative property underpins data integrity and safeguards against malevolent modifications. To illustrate the implications of collision attacks, the speaker employs a simple scenario where Oscar endeavors to surreptitiously alter a bank transfer sum from €10 to 10,000 euros while preserving the congruous hash output. To vividly illuminate the ramifications of collision attacks, the speaker draws an analogy to the celebrated birthday paradox. This paradox elucidates the counterintuitive phenomenon that within a specific group of individuals, the probability of two individuals sharing the same birthday is unexpectedly high. For a more nuanced comprehension of collision probabilities, Professor Paar introduces a formula wherein T designates the number of inputs and N symbolizes the magnitude of the output space. This mathematical expression facilitates the computation of collision probabilities. From 40 minutes to 45 minutes of the video, Professor Paar elucidates the concept of collision attacks, a significant vulnerability within the realm of hash functions. He contrasts these attacks with second preimage attacks, emphasizing the increased complexity and resilience required to thwart collision attacks. To illustrate the principle of collisions, he employs the well-known birthday paradox, a thought experiment involving a party and the probability of two attendees sharing the same birthday. The audience's initial estimate of 180 guests, while close, underscores the counterintuitive nature of the paradox, as the actual average number required for a 50% chance of a collision is 365. Paar then delves into a more formal mathematical exposition, introducing the concepts of input and output spaces within a hash function. He asserts that collisions are inevitable when the input space's cardinality, or size, surpasses that of the output space. This is exemplified using a hash function with an output of 160 bits, where the necessary number of inputs for a 50% collision probability is 2*160/2, or 2 to the power of 80. This underscores the importance of doubling the bit length of the output to achieve a secure hash function. The professor concludes this section by emphasizing the critical role of collisions in modern cryptography, promising a more comprehensive exploration in the following week's lecture. In the YouTube video titled Lecture 20, Hash Functions by Christof Paar, Professor Paar elucidates the imperative for hash functions to possess swift execution speeds, thereby circumventing computationally demanding operations. Employing the illustrative example of signing a 50-gigabyte hard drive using RSA exponentiation, a process estimated to consume approximately 1 million hours, he underscores the inefficiencies inherent in utilizing asymmetric algorithms for substantial data volumes. To vividly illuminate the inherent challenges, Professor Paar presents a scenario in which an adversary intercepts a message secured by an RSA signature. In this scenario, the attacker possesses the ability to manipulate the message while still ensuring the signature's validation. This vulnerability arises from the signature's application to a limited portion of the message, specifically a 256-byte block. Addressing this deficiency, Professor Paar introduces the concept of hash functions, algorithms designed to compress lengthy messages into smaller outputs of fixed length. This abridged output, termed a message digest, subsequently undergoes signing using the private key. Professor Paar emphasizes the significant speed advantage of this approach compared to directly signing the entire message. Professor Paar proceeds to discuss the fundamental security property of hash functions known as preimage resistance. Preimage resistance signifies that given the hash output, reconstructing the original message should prove computationally infeasible. This property is paramount for applications such as key derivation, where safeguarding the original key from compromise is critical. Moving on to second preimage resistance, Professor Paar explains that this property ensures an attacker's inability to discover an alternative message possessing the same hash output as a given message. This property holds particular significance in the context of digital signatures, as it thwarts the forging of signatures for messages not originating from the attacker. Finally, Professor Paar delves into the most intricate and vital aspect of hash functions: collision resistance. Collision resistance implies that it is exceptionally difficult for an attacker to uncover two distinct messages yielding identical hash outputs. Professor Paar clarifies that while hash functions cannot be engineered to eliminate collisions entirely, the objective is to render their discovery extremely challenging. This objective is achieved by ensuring a hash space significantly larger than the input space. From 50 minutes to 55 minutes of the video, the speaker delves into the ramifications of the pigeonhole principle in the context of hash functions. He lucidly explains that due to the input space being significantly larger than the output space, collisions are inevitable. This implies that constructing a hash function entirely devoid of collisions is an impossibility. To illustrate this point, he utilizes the familiar analogy of a party where the input space is represented by the number of individuals invited, and the output space corresponds to the number of days within a year, 365. Through this analogy, he demonstrates that to achieve a 50% probability of a birthday collision, one would need to invite 23 individuals to the party. The speaker subsequently elaborates on the concept of a collision attack, wherein an attacker seeks to identify two distinct inputs that map to the same hash output. He emphasizes that if the output length were to be 80 bits, the attack would demand 2 raised to the power of 80 steps. However, due to the inherent nature of the birthday paradox, the discovery of a collision requires substantially fewer steps, specifically the square root of that aforementioned figure. He once again employs the party analogy to solidify this concept. If the process of finding a collision with a specific day, e.g. July 18th, necessitates 1 million steps, then finding a collision with any day throughout the year would require only the square root of 1 million, which translates to 1,000 steps. This effectively highlights the significantly reduced complexity of collision attacks compared to pre-image attacks. From 55 minutes to 60 minutes of the video, Professor Paar delves into the significance of the birthday paradox, a pivotal concept in understanding collision attacks within the realm of hash functions. He expounds on the notion that to mitigate a 50% probability of collision occurrence, one necessitates a hash function with an output bit length twice that of the intended output. He employs an illustrative scenario involving an 80-bit output, demonstrating that an attacker would require 2 to the power of 80 hash computations to identify a collision. Professor Paar underscores the considerably lower computational burden associated with collision attacks compared to second pre-image attacks. Subsequently, he elucidates the intricate connection between collision attacks and the birthday paradox. Professor Paar clarifies that given T inputs, the likelihood of encountering a collision can be precisely determined using a specific mathematical formula. He concludes this segment by emphasizing the complexity of the underlying mathematical principles and urging the audience to meticulously engage with the lecture notes. From 60 minutes to 65 minutes of the video, Professor Paar transitions from the introduction of hash functions to a deeper exploration of their security properties, specifically focusing on the crucial concept of collision resistance. He contrasts this property with pre-image resistance, emphasizing that collision attacks do not require prior knowledge of the original message, unlike pre-image attacks. He demonstrates that a hash function with an 80-bit output would necessitate approximately 2 raised to the power of 80 computational steps to locate a collision. However, he then unveils a significant insight. Achieving the same level of cryptographic strength against collision attacks mandates twice the output bit length, requiring 160 bits. This counterintuitive principle is attributed to the birthday paradox, a probabilistic phenomenon where the likelihood of 2 individuals sharing the same birthday within a group grows exponentially with the size of the group. Professor Paar uses the birthday paradox as a tangible analogy, illustrating that with a gathering of 23 individuals, there's a 50% probability of a shared birthday. He emphasizes that this principle directly applies to hash functions, implying that finding a collision requires only the square root of the total number of potential outputs. This means a hash function with 2 raised to the power of 160 possible outputs becomes susceptible to collisions after merely 2 raised to the power of 80 computational steps. To further illuminate the potential vulnerabilities of hash functions, Professor Paar provides a compelling example of a collision attack. He demonstrates how an attacker could exploit the weaknesses of a hash function by locating 2 distinct messages that map to the same hash value. He reveals how an attacker could strategically manipulate a message to generate a collision, even without access to the original message, highlighting the critical need for robust hash functions with sufficiently long output lengths to mitigate these risks. Professor Paar concludes this segment by underscoring the considerable importance of collision attacks in the realm of cryptography. He asserts that the robustness of hash functions hinges on their resistance to these attacks. He concludes by signaling that the discussion of hash functions and their properties will continue in the following week's lecture, inviting the audience to remain engaged with this critical topic. From 65 minutes to 65 minutes of the video, Professor Paar illustrates that the security of a hash function with an 80-bit output against collision attacks is significantly lower than initially perceived. He emphasizes that while finding a collision would theoretically require 2 steps, this is a misrepresentation of the true vulnerability. This stems from the inherent probabilistic nature of hash functions. Each new input yields a seemingly random 80-bit output. To elaborate, Professor Paar presents a thought experiment. He asks the audience to estimate the number of guests required at a party to ensure a 50% probability of 2 attendees sharing the same birthday. He reveals that the answer is 23 individuals, which is remarkably close to the square root of 365, the number of days in a year. This exemplifies that, contrary to the initial assumption of 2 steps, a collision attack against a hash function can be successfully executed with significantly fewer attempts, in this case, approximately the square root of the number of potential outputs.